This video is about gravitational potential energy. Let's begin by recalling the gravitational potential energy formula that we learned in subtopic 8.3. Here, delta EP is change in gravitational potential energy, m is the mass of an object moving in a gravitational field, g is the gravitational field strength, or the acceleration of free fall, and delta h is the vertical height through which the object moves in the field. In calculations, we almost exclusively use this formula near the surface of Earth when an object moves through a certain vertical height. Near the surface of Earth, the value of g is approximately 9.8, and its unit is either meters per second squared or newtons per kilogram. Now imagine that we want to work with gravitational potential energy not only near the surface of Earth, but over much larger distances. Unfortunately, for large distances, this formula does not work because gravitational field strength varies with distance. Near the surface of Earth, we can assume that the gravitational field is uniform, and because gravitational potential energy always arises due to two masses, and in the formula above, the mass of Earth is included in g. So let's see how gravitational potential energy works in a situation where two masses are separated by a large distance. In fact, initially we'll assume that the separation between these two masses is infinite. Of course, an infinite separation is theoretical, however, it does help us develop a definition for gravitational potential energy. We learned earlier that the gravitational force between two objects is inversely proportional to the square of the distance between the objects. From this it follows that when the separation of two objects is infinite, no gravitational force acts between the objects. Now imagine that we start moving one of the objects closer to the other at a constant speed. Let's assume that here we are moving m2 closer to m1. It is important that we are moving m2 at a constant speed. Let's think about the forces that act on m2 in this situation. Now as soon as we start moving m2 towards m1, the separation between the masses becomes finite. Therefore now, m1 does exert a gravitational force on m2. This force is attractive, so it is pointing towards m1, and I will denote this force as Fg. Of course, according to Newton's third law, m2 also exerts a force on m1 in the opposite direction that has the same magnitude as the first force that we have drawn. Now as m2 is moving at constant speed, there must be another force that acts on m2, pointing to the right. In addition, the magnitude of this force must also be Fg. I will denote this force as Fa for applied force. This force must be applied on m2 to ensure that it does not accelerate to the left. If it helps you better visualize the situation, you can imagine that you are lowering a bucket full of water from the top of a building using a rope. It would take some effort on your part to lower this bucket at a constant speed, and this is so because you'd need to balance the gravitational force that is trying to accelerate the bucket downwards. Hence, in the process, you would be doing some work on the bucket. Similarly, in our situation here, force Fa is doing work on m2 as the two masses are brought closer together. Gravitational potential energy is defined based on this work done. One way to write this definition is that the gravitational potential energy of two masses is the work done when bringing the two masses from an infinite separation to their current position. In our final step, we'll deduce the gravitational potential energy formula, and to do this, we'll assume that after m2 has been moved, the new separation of the masses is r. To begin, we'll use the gravitational force formula to write that the gravitational force between the masses is g times m1 times m2 divided by r squared. Remember that g here is the gravitational constant. In general, the work done by a constant force when moving an object is equal to the force multiplied by the distance over which the object was moved. However, here, as we move the masses closer to each other, the gravitational force increases, so it is not constant. Therefore, to calculate the work done by force Fa on m2, we need to use integration. You do not need to know or understand the mathematical details of how this integration works, so I will just briefly write down that the work done in this situation is equal to the definite integral from infinity to r of the gravitational force, so g m1 m2 over r squared, with respect to r. The key takeaway for us is that the result of this integration is negative g m1 m2 over r, which is the work done by Fa when bringing the two masses from an infinite separation to their current position. Therefore, based on our definition below, this work done is equal to the gravitational potential energy of the two masses. We'll also add the table with a list of the variables. To complete our learning, let's take a moment to talk about the negative sign that you see in the gravitational potential energy formula. Since G, M1, M2, and R are all positive values, we can conclude that the gravitational potential energy is always negative. There's one exception to this, because at an infinite separation, the gravitational potential energy of the two objects is zero. If you think about it, this also makes sense based on the formula that we just learned, because if R is infinitely large, then the value of the fraction G times M1 times M2 over R can be taken as zero. Now when the separation of two objects is finite, a gravitational force acts between the objects, so in order to move the objects to an infinite separation, in other words to a position where the gravitational potential energy of the objects is zero, we need to do work against this gravitational force, which means transferring a positive quantity of energy into the system. Since this energy transfer raises the gravitational potential energy of the system to zero, gravitational potential energy before the transfer must have been negative. This was one way to explain the negative sign in the formula that we just learned. With this, we have completed our video about gravitational potential energy.